So welcome everyone. Thank you for joining the webinar 30 Years of Climate Change Science. What do we know and not know about hydrologic change in the Finger Lakes? My name is Caitlin Fellow. I'm the Association Director of Seneca Lake Pure Waters Association. Recently, we've been talking a lot about climate change, and our mission is a lake association. How do we engage in the important conversation of climate change, and how do we take action with community leaders and residents to create change within our own watershed? The issue of climate change sometimes can feel very grand and feel like the problem of solving the issue is completely out of our control. But we know through others' actions that there are teachable and meaningful techniques to protect ourselves and make our communities more resilient to the effects of climate change. And Pure Waters is now working on a strategy to implement climate change education and resiliency programs. Of course, to create a new program, we have plenty to learn, and this presentation will be a great introduction. Could not have come at a better time. We've had a lot of interest in this webinar, and I'm sure there will be a lot of questions during our Q&A session at the end of the presentation. So with that, I'd like to introduce our speaker tonight, Professor Steve Shaw. Steve is an associate professor at SUNY ESI, Environmental Resource Engineering. Steve's research falls within the topic of impacts to water resources in a changing climate. Specifically, his research topics include building climate resiliency within agricultural systems, investigating technologies to mitigate small-scale localized HABs, and fundamental physical hydrological processes. I will add Steve's research page link into the chat box for those who are interested in learning more about his research. With that, I welcome Steve Shaw. Thank you.
Hi, everyone. Thanks for having me tonight. So my talk isn't comprehensive, even though the title kind of makes it sound like it could be. It's really sort of more of a story of how do we know what we know about climate change and about science. So what I want to start with, in some ways, this the broader theme is just to kind of, I guess I can't exactly take a poll, but this is a statement from the Intergovernmental Panel on Climate Change, which says, based on current model results, we predict an average rate of increase of global mean temperature during the next century of about 0.3 degrees Celsius per decade. This is a more rapid increase than seen over the past 10,000 years. And then it goes on. But just to think to yourself for a few seconds, when do you think this statement was written? Is that a recent statement, or is that one that's been around for a while? So if we look at when this was written, this was actually written in 1991. Really, so for more than 30 years, in some ways, at a broad scale, we've been saying the same thing. Scientists have recognized that there'll be climate change at a global scale.
I'm listening to.
On a policy side, we haven't quite.
Just let you know.
But at the same time, scientists have basically been studying what are the implications of that at a regional scale. So what I want to talk about tonight is first actually just sort of make the case for why there is global climate change at the global scale. Just take a few minutes to do that. I kind of see this just as a educational opportunity to kind of remind people of sort of the facts and the concepts underlying that, which I think sometimes we don't hear that enough. But then what I want to spend most of our time on is this more of the implications for the Finger Lakes. And so basically understanding and talking about regional changes in climate and hydrology. And I really could have called this talk basically, will there be more flooding in the Finger Lakes in the next 100 years? In essence, that's what I'm ultimately going to talk about. But I sort of want to talk through sort of the process of building that knowledge. What do we know and not know about that still, if there will be or won't be more flooding, and the magnitude of that. And then I'll just take a few minutes at the end to basically talk about, as you'll see, there's still uncertainties about what will happen. How do we still not be paralyzed, but still come up with policies and ways to react to potential changes? Okay, so what I wanted to start with, and as we'll see, sort of this talk is partially about sort of our confidence level in the information we know. So as we're going to kind of go through this, we'll sort of lay out the evidence for why we have high confidence in climate change at a global scale when we look at things averaged over the globe. But then when we start to talk about regional changes, we have sort of more moderate or more limited confidence. So at the global scale, the place to start is what I would kind of refer to. I just gave this lecture in class today. So my first day of class is, if we're going to explain anthropogenic climate change, we kind of have 4 pillars to it. And any one of them can sort of partially make the case, but the 4 of them together are sort of the strongest way to make the case. So sort of the first one is sort of, what are we seeing that really give an indication this is happening? And really, that's just the simplest thing, is just to say, let's look at temperature, right? So when we look at temperature, we see that over basically the last 50 years, if you measure temperature and average it over the entire globe, you've had about a 1 degree increase in temperature. And you might say, well, it doesn't seem like that much. And on any given day, you can have, moderate swings in temperature, way more than 1 degree. But this is at a global scale, and especially when we look at this in the context of how has temperature changed globally. This is just the last 1,000 years. But when we put it in this context, we see, and I sort of extended the record a little bit with that red line there, just to get up to 2020. But we basically see in the temperature change we've seen in recent years is sort of the most rapid change we've seen for 1,000 years, and actually going back tens of thousands of years before that, right? So this really rapid and extreme change. So now we know this, we know the climate is warming, but we might say, well, how do we know that's due to humans? So we need to link to it something causal. Right, so what we have there, this recognition that at least moving in an upward direction at the same time is greenhouse gas emissions, which the primary one we think about is carbon dioxide. The most sort of, I wouldn't say reliable record, but I guess robust record we have is carbon dioxide measured at Mauna Loa Observatory in Hawaii. There's a good reason it's there. Originally, it was started in 1958, really before anybody was thinking about climate change. It was a scientist, this is called the Keeling curve. So it was Keeling, who was studying other things, but he was interested in basically atmospheric CO2, and decided that putting it out on an island in Hawaii would be a good way to isolate from other influences you might get on land. Right? And it wasn't really until the 80s or so where people realized sort of what a valuable data set this was in terms of documenting what humans have been doing to the atmosphere and how that carbon dioxide has been going up. And here's a picture of the observatory on this mountaintop out in Hawaii, isolated from most other influences nearby. So we have our first 2 parts. We know temperatures going up. We basically know correlated to that is increases in greenhouse gases, with CO2 being the primary one. But what we really want is we want some physics behind that. What's sort of the causal linkage that says increases in CO2 should increase temperature? So we've understood to some degree these physics for over 150 years. So what I show here is just a little sketch of an experiment done by a British scientist, John Tyndall, in 1859. And I'll show another picture of some of the actual instruments here, but this would be sort of rudimentary by our standards today. But he was basically had 3 components to this. He was basically generating infrared rays. So basically sort of a heat source to generate these infrared rays. He was passing it through a gas chamber, this wooden tube here, where he could put in different types of gases, and then he could basically measure how much of those rays came out the other end, how much of those infrared radiation came out the other end, and basically see if any of those, if the gases were trapping any of those radiative waves passing through. So this is the wooden chamber he used. Right, it almost looks like a part of a table or something like this, but this was his way of trapping gases, and then he was passing and then measuring how much was coming out the other end. Sorry, and then he had, here's my the quote at the bottom here. I was indeed slow to believe it possible that something as transparent to light as ethane, a olefiant gas, was densely opaque to any kind of calorific infrared light. And to secure myself against air, I made several hundred experiments with this single substance. So really someone operating not specifically with CO2, but with other gases, purely out of kind of scientific curiosity, and laying the foundation for understanding that gases, which seem totally transparent to light, can actually trap that energy. And just a point I like to make was, this was sort of before there were any sort of politics surrounding climate change done, more than 150 years ago to sort of lay this physical basis linking CO2 and temperature. And then the final piece we kind of need to make the case is, will this continue into the future? Right, so how would we done that? Basically by modeling. And I don't have a really good slide for this, but basically since the 1940s, humans have expended a huge amount of energy developing models and developing computers and sensors and ways to basically measure climate, to test the models, to sort of validate that we have models that can model future climate. And what those models show is really at a range of different sort of emission scenarios, depending on greenhouse gases, but undeniably that there'll be increase in global temperature. And there's multiple models from different modeling groups in different parts of the world, and they basically, for the most part, all show the same thing, which is upward increases in temperature. Okay, so that was really a little just foray into just to remind ourselves, why do we know what we know when we think about climate at a global scale? And we can say we have very strong certainty in terms of change in temperature at the global scale. But what we're really interested oftentimes is what happens to our own communities immediately around us, right? So we're not talking about changes at global scale, but we're talking about changes at what I refer to as regional scales. So what I'm going to talk about the rest of the talk is basically what are changes in precipitation, so basically rainfall, and what are changes then, how does flooding relate to that? And how do we understand that both historically and for the future? So I'm going to start with precipitation. So every few years, there's a national climate assessment. And this was maybe 6-7 years ago. This slide came out in a climate assessment. And people, especially scientists, in terms of sort of making the case for concern, really like to show this slide. I was at a conference once where everybody that stood up showed this slide as their intro for why we should be concerned. And what this is very clearly jumps out at you. It's saying, observe changes in heavy precipitation in the Northeast, 71% increase in those changes, right? The thing that what we'll talk about a little bit is, well, what does this mean in terms of implications, right? In terms of flooding, because in some ways, and this goes to the what's known and unknown. Does this imply that flooding itself will increase by 71%? But it definitely implies that there's something going on with precipitation, which is upward. So if we look at this in a little different context, this is from a number of different reports from the US federal government and then from different global agencies. So this is again from the IPCC, so the Intergovernmental Panel on Climate Change. And what they're looking at here is they're saying, what is the likelihood of having a flooding event that's intense enough such that it only happens on average every 10 years. So sometimes we talk about return period flood events. So this one is talking about a 10-year return period flood event. So on average, it happens every 10 years. And it's basically, or a precipitation event. And it's a precipitation event where we're measuring precipitation over one day. And here, just to give some sense of sort of magnitude of change, they're saying if we have 2-degree increase in temperature, which might occur by the middle of the century, by 2050 or so, we'd be about 1.7 times more likely to have this 10-year, one-day event, which certainly shows an increase. But then this starts to get into sort of the details of this. Like, is it basically every year we're going to have some catastrophic event? Well, not quite, right? And just to give some context for this in specific detail, so if we go to Elmira, which has a long-term meteorological station, a 10-year, 24-hour event, which is the kind we've been talking about here, is 3.84 inches of rainfall. So basically that would occur instead of every 10 years, maybe more like every 7 years. And then other ways of showing this too. So this is actually showing a sharp change in sort of the 1970s. For this is daily precipitation above the 90th percentile. So just another way for the entire Northeast quadrant. So other evidence of increases in precipitation. And when you look at sort of what the IPCC says, again, this is their sort of official statement on things. They'll say that it is very likely that heavy precipitation events will intensify and become more frequent in most regions with additional global warming. And then they'll specifically say that precipitation will intensify about 7% for each 1 degree C of global warming with very high confidence. Right? So part of the question here is, how can they be so confident about that? Where does that high confidence come from? And this is where we get really into details, intensify about 7% for each 1 degree C of global warming. So it's one reason they can be so confident about that. The main reason is because this goes back to really simple physics for what's going on, or chemistry. So it's referred to as the Clausius-Clapeyron relationship. But what you can really think about is if you have two containers of, say, a plastic bottle that you've drank most of the water out of it, but there's a little bit of water left in the bottom. If you were to put that out in the sun and then basically see how much of that water evaporated in the bottle, different things would happen at different temperatures. If it was 10 degrees out, you'd get a lesser fraction of water vapor evaporate in that bottle versus, say, if it was 20 degrees out. If it was 20 degrees out, you'd get more than twice as much evaporate in that bottle. So based on that same principle, if we think of the atmosphere as a giant bottle that can be heated at different temperatures, if we can heat the atmosphere to a higher temperature, we basically can get more water vapor in the atmosphere. And then when it rains, you have more water vapor that's available to come out of the atmosphere. And this was developed just at a sort of a laboratory scale, right? Just as I sort of described, people looking at water vapor basically in flasks or something like that. But at the same time, it basically scales the same way for atmospherically. So this is a little busy, and this is from an academic paper and not, I guess, necessarily meant for, widespread distribution. But what this is showing is so the CC here refers to as the Clausius-Clapeyron relationship. It's taking rainfall events that aren't very likely to occur, so 99.9 percentile, right? So occurs like 1 out of 1,000 times. And it's showing how does that scale the magnitude of that event? How does it scale with temperature? And then it's doing this for different weather stations in New York. And really, it's only in the last 10 years or so that meteorologists and climatologists have sort of acknowledged that this Clausius-Clapeyron scaling actually does a really good job sort of providing a bound for how much you would expect rainfall intensity to change. Because you can imagine a storm event includes the interaction of lots of different processes. One of those is just how much moisture the atmosphere can hold. So I think people initially were sort of reluctant to say this explains, how intense rainfall will scale. But now it's become kind of widely accepted, and thus the statement from the IPCC that we expect rainfall intensity to increase 7% per degree C. So there's some conditions to which this apply. So as I sort of said, storms have multiple different processes that interact to make the storm occur. So it applies most to shorter storms, because it basically is saying that if you have your atmosphere can hold more moisture. If you have a storm, though, that's not dependent on just the moisture immediately in the atmosphere. So I show over here on the left-hand side, a short storm, this bucket is basically just dumping the water that's just right there, right overhead. Whereas a long storm, we think of it as a mechanism to basically draw in moisture from potentially hundreds of miles away. So I show this as sort of a conveyor belt with buckets on it, and it's sort of drawing in moisture, and it's not dependent on only what's right there. So as we go from basically shorter storms, where this Clausius-Clapeyron relationship, the 7% increase really holds up, to longer storms, which really, it seems like it holds up to about 24 hours, but beyond that, then other mechanisms take over. But it does apply at these shorter scales. Okay, so given that we've sort of identified, really scientists have sort of collectively agreed, really in just the last 10 years, that the Clausius-Clapeyron relationship is a pretty reasonable way to look at sort of high intensity, the frequency of high intensity events and how that might change. What we want to talk about next is how does that actually relate to flooding? And given that we know we've had warming, we've had about, as I showed early on, about 1 degree of warming, at least globally in the last 50 years. And we know we should have had increases in precipitation intensity, which we can also show. Do we actually see increases in flooding frequency? So to do that, the easiest thing to do is to go look at some data. So there's the US Geological Survey. in the US, which measures around over 10,000 streams and rivers across the United States. A lot of these measured for over 100 years. So I looked at data for two, basically a river and a creek in the Finger Lakes region that have over 100 years of data. So what this shows is it's annual peak daily flows. So each year has 1 point, and that 1 point is basically the maximum value measured. So the highest value at any point during the year, right? So if you have your highest flow on June 15th in 1919, that one value becomes the point on the graph. And then if you have your highest flow on January 3rd in 1920, that 1 point becomes the point on the graph. So then when we can look at this is basically, does the magnitude of these annual peaks change over time? And at least for the Cohocton River, they don't, right? And actually, so I put a trend on here. It's not statistically significant, but it is actually slightly downward. So we'd actually say it looks like flooding magnitude is actually becoming slightly lower. And then we can look at, so here's another example, Fall Creek. This is actually a smaller watershed. It outlets kind of near Ithaca on Cayuga Lake. And again, here we see a few large peaks, especially earlier in the record, but really nothing large in recent time. And again, it actually seems like the trend is somewhat negative, slightly, not significant though. Right, so we kind of have then this issue of, we know precipitation is going up, we know precipitation intensities are increasing, but at the same time, when we look at stream flow records, we seem to see that there's no indication yet that flooding has increased. So the question is sort of, what's going on here? What might we be missing? So I want to sort of talk through that. And this is actually then where we connect back to sort of, especially when we start to think about what's happening close to the Finger Lakes. And we'll work up toward actually think, if people remember the flood of 2018 on Seneca Lake, which was a really intense, pretty damaging flood, to kind of put that in some context of why is something like that not showing up in these records. So the first thing to think about is sort of how do we conceptualize flooding? And in a very simple way, people often just equate precipitation intensity to flood intensity. That if you have more rainfall, it happens more quickly, then you should have higher flows in your stream, right? And people have used this sort of simple model over and over, and sometimes it works and sometimes it doesn't. What's more reasonable, and this is what we'll kind of talk through, and sort of why precipitation increases haven't necessarily translated into peak flow increases, is because really flooding is dependent on more things. So I have here, it's dependent on precipitation intensity, but it's also dependent on the duration of the precipitation, features of the watershed, also potentially snow, things like how wet is the watershed before it starts raining. So what I want to do is walk through some of these different features and sort of make the case that, well, we might have relatively high confidence precipitation intensity will increase. To predict flooding, we need to understand what's going on with these other features, these other components that influence flooding. So I'm just going to briefly talk about sort of groups of these. So the first one, I'm just going to talk about basically some different watershed processes. So this is a little bit outside the Finger Lakes, but what this is showing, again, this is showing peak flows over time for the Delaware River. And in the early to mid 2000s, there were 3 really large flood events on the Delaware River, basically consecutively, one year after another. And they were basically 100-year return period events. They were 3 events you'd really only expect on average every 100 years, but those 3 events occurred 3 years in a row. And people looked at those and said, is this the start of something, a new normal? Sometimes you hear that terminology when talking about climate change. Did we just shift somehow in terms of sort of the processes influencing our river? So a scientist from Princeton, Jim Smith, who's basically kind of had a whole career of analyzing flooding, did something relatively simple, which was basically step back and say, let's classify sort of what caused those peaks. So he looked at, was it snowmelt? So he basically just said, did this peak occur in the springtime? And then he said, if it didn't occur in the springtime, did it occur in the summertime? Which would imply it was caused by thunderstorms. And then as a third category, he said, let's look at storm tracks And when we have tropical storms, let's label something as a tropical storm. So when he looked at those 3 events in the mid-2000s, even though they were all sort of the same magnitude and much higher than a lot of other events that had happened in the past, they were for 3 totally different reasons. One was a spring snowmelt, one was basically a remnants of a tropical storm, and one was a series of summer thunderstorms, right? So it's one of these things that when you start to dig into causation, you realize it's more complicated. One particularly sort of interesting aspect of this is back to this idea of, can we relate rainfall to flow, to discharge? That is, rainfall intensity increases, does stream intensity increase? So what this chart shows is in the light gray, and what I have labeled rainfall 1, rainfall 2, rainfall 3, it's showing rainfall events and basic intensity on different days. And then the lines are showing the stream flow that results from that. And what we can see is basically it rains really intensely on June 26th, and not much happens in the stream. And then it rains really intensely on early June 27th. And it starts to respond a little bit. And then it rains again on around midday, June 27th. It starts to respond quite a bit more, and then it rains one more time on June 28th, and then it really responds. And what this is showing here is it's not so much just the intensity of the rainfall, but it's basically the accumulation of rainfall, and you start to have a watershed that's so wet, it can't hold many more rain, right? So if we just simply look at rainfall intensity, which is often what people just measure, how much rain in 24 hours, it's not going to represent sort of what actually happens here to cause flooding. Okay, so that's sort of one part of sort of this complexity of relating precipitation to flooding. The other one has to do with more of the watershed itself. So let's talk about watersheds and a little bit about how precipitation is measured relative to watersheds. So the first thing, just to kind of remind ourselves, is precipitation is measured at a point, right? And this is the meteorological station at Game Farm Road over in Ithaca. The precipitation gauge itself, where you actually measure the rain, it's only 8 inches across, right? And what we do, we take precipitation and we basically, in most cases, we assume that that measurement on this gauge that's only 8 inches across is representative of precipitation across an entire watershed, which might be tens of miles across, right? So here I show our watershed area. The rain gauge is just the sort of the orange circle. And then the stream flow that comes out of that, which would be related to the flooding, right, is really an aggregate measurement of all the rainfall that fell in there. So there's some very simple things that become obvious that could be happening, right? So here I found a nice map of the Seneca Lake watershed, and this is merely representative, not necessarily indicating anything specific. And I don't think this rain gauge doesn't actually exist here, just simply just as a matter of illustration. But you could have a rain gauge sort of shown by this yellow star here, and you could have basically a small storm pass over it that would give the appearance of you had a lot of rain, but really most of the watershed didn't see all that rain, right? And a single rain gauge doesn't tell you anything about extent. At the same time, you could have a much larger storm, and in this case, the entire watershed actually sees that entire storm. But these are sort of the imperfections of the data we work with oftentimes, where if you look at just rainfall records alone, they don't really tell you about the extent of the storm. Is it large enough to influence a relatively large watershed? The other thing hydrologists specifically think about in terms of linkage between rainfall and flooding is the duration of the rainfall relative to the size of the watershed. So to sort of explain what's going on here, so hydrologists have this terminology of this idea of what's called the time of concentration. So say you have 2 houses, right? So these nice yellow houses, they look kind of out of place in the Finger Lakes, somewhere more tropical maybe. But they have 2 roofs of equal size and equal slope. But one is sort of a more modern house over here on the left side, right? And this roof is just a 1-pitch roof, right? This other roof, same area, but basically 2 pitches. On both of these roofs, there's a gutter that's collecting the rainfall. If you were to measure how much runoff you have in that gutter, you would see 2 different things. On the roof with 2 pitches, right? Basically, the rain will reach the gutters faster. It doesn't have to travel as far. So if we were to measure what we call the time of concentration, how long does it take to hit its peak runoff rate? It happens in 5 minutes, say for this roof with 2 pitches. This roof with 1 pitch, because the rainfall has to travel twice as far from the very highest point on the roof, the time of concentration is 10 minutes. So in order to sort of achieve sort of peak flow from a rainfall event has to last at least as long as the time of concentration in the watershed, right? So if we have a storm that only lasts 5 minutes, for the house over here, we would get to our peak rainfall runoff rate because the time of concentration is 5 minutes. For a storm, for the other house, or more modern house, if the storm only lasts 5 minutes but the time of concentration is 10 minutes, we never hit the peak rate. So the same thing happens in watersheds, right? For smaller watersheds, we often hit the time of concentration. But for larger watersheds, a storm might not last long enough that we actually reach the time of concentration. So even though we can have really intense rainfall, it's not actually long enough for the entire watershed area to be contributing to the outlet where you're measuring that flow. Okay, so this sort of brings us to sort of a bit of a case study of what sort of might have gone on or what went on. So this intense event in August 2018 near Lodi, New York. In some ways, why could this maybe be a flooding event sort of indicative of climate change, even though our other records of stream flow don't really show any trend? So first thing to know is, I don't have the watershed area, but this is a relatively small watershed. Just like a lot of the streams on the Finger Lakes, we're talking about relatively small, steep watersheds. So this was sort of the outlet on the lake side, and we can see things got totally inundated. If we look at the nature of the storm, so I went back and I pulled radar data that really helps us see sort of the extent of the storm over time for this particular one. So this was all happening in the middle of the night, 1 in the morning. So I put Watkins Glen in here just to give a sense, southern end of the lake, sort of how is this storm evolving, right? So this is 1 a.m. in the morning. This is 2 a.m., right? So the storm is still sort of centered over Seneca Lake, the lower part of Seneca Lake. The intensity, the colors are showing different intensities. So green and blue are really modern intensities, yellow and oranges are sort of higher intensities, and then red, where you see that as really high intensity. And this is all from radar data, so that's how we can see this spatial extent. So by 3 a.m., still sitting over Seneca Lake, and we particularly see these high red intensities kind of over where Lodi is on the east side of the lake. And then 4 a.m., the highest intensities again are basically right over Lodi. Right. So when you look at this in this series, it's not really surprising that you had a flood event. There's a few things to take from this, right, in terms of the context of this. First thing is to actually look at how much was measured. So if we look at what was measured in Mecklenberg, sort of more south, kind of over by Watkins Glen, it was 3.8 inches. If we look at Penn Yan, it was only about 1 inch. If we look at Aurora, which is over in the mid side of Cayuga Lake, it's only 1/2 inch. And then only if we measure at Dundee, we see 9 inches of rain. But what we see is a really pretty spatially localized high intensity event. So if we relate to some of the concepts I was talking about, it would be large enough extent to reach the time of concentration of a small watershed. But if you took this same event and put it over, say, the Chemung River that we were looking at before, or even Fall Creek near Ithaca, it probably didn't last long enough and didn't extend far enough to actually reach the time of concentration and to fully cover those other watersheds. And as I sort of explained earlier, when we're thinking about where do we have the most confidence for how rainfall intensities will change, it'll basically be for relatively smaller and shorter duration rainfall events. To also put in context about this 8.75 inches measured, this is basically over 4 hours. The Northeast Regional Climate Center, which is based in Ithaca at Cornell, actually has done predictions of how rainfall intensities might change by the end of the 21st century. And their sort of 100-year return period rainfall intensity for Elmira is 4.2 inches. So this 8.75 is really off the chart. So it's not even within the range of what you might anticipate with climate change. We might say this is probably like on the order of a 500-year, 1,000-year return period event, right? So it's not even sort of the marginal change you might expect with climate change. It's a huge event that's really even outside of what you would ever expect with sort of just by climate change alone. But my main message with all this is just partially just to show the complexity that goes into translating precipitation changes to outflow, to flooding. But the simple message is that smaller watersheds might be more susceptible to increases in precipitation intensity than larger watersheds. Whereas when we look at streamflow records, we mostly look at larger watersheds, but what we probably don't fully represent is these smaller watersheds. One thing just to start to wrap this up a little is just to ask, is there evidence of past disruptive flooding of maybe of this magnitude that we saw in 2018? And I had never really thought about it that much until I was giving this talk, but if you start to look at, are there features in the lake and where do they happen? I'm not a geomorphologist, I don't do this all the time, but we can start to say, well, where do these points on the lakeshore come from? And oftentimes where the way they likely formed was basically erosion from the land surface, right? So basically you had enough erosion and enough flooded water or flowing water to basically erode material out and form that point. So there's clear evidence that the flood we saw in 2018 over the geologic history of the lake isn't unusual. You would have had to have something like that for those points to even form over time. And just within the record, have we ever seen anything like that? Is that flood in 2018 purely something that's caused by climate change? Can we even make that attribution? And we have seen events like this before, and probably actually even more severe. So in 1935, there's an event that basically extended from around Ithaca all the way over to, I think that's Sullivan County, and basically had rainfall intensities of over 10 inches in the period of time. So if we sort of try to say, is that event in Lodi something unique? No, not necessarily. We have seen it before. I'm going to skip these. So what I want to just sort of, as I start to sort of wrap things up, go back to this question of what do we know and not know? And basically this idea of we can't just take sort of simple assumptions and translate those into sort of outcomes. So we might be sort of tempted to say that increases in rainfall intensity should lead to increases in flooding, but it's not always a simple thing to do that. So just to step back through this, so we basically the strongest physical argument for increased precipitation is at sort of a sub-daily scale for shorter events that last, say, 3, 4, 5, 6 hours, something like that. And then flooding itself is dependent on all sorts of things besides just the rainfall amount. It's dependent on how wet is the watershed you start with, what's the watershed size versus the storm size, what type of precipitation is it. Model changes in precipitation, well, that's the one thing I skipped over, I'll avoid that. And then some of our perceptions of change might be more due to the way we use high-risk areas. And that actually goes back to those points and the shorelines are good evidence of erosion in the past, but they also become convenient places to basically build houses or to go as a place to enjoy the lake. But we're actually putting ourselves potentially at risk by using those areas where we know there's been flooding in the past. Okay, so sort of back to where we started from. High certainty for global climate change. When we start to talk about more regional changes, we have pretty moderate certainty of increases in precipitation, moderate to high. But then how that translates into changes in flooding, I say it's conditional certainty. And it's basically conditional in both the scale of the flooding event and sort of the scale of the watershed. And what I would sort of say, I don't have this in the text here, is that if we have a small watershed at sort of the scale of many of the streams that feed the Finger Lakes, we probably have a relatively high confidence you might see higher flow events there. If you have a bigger watershed, say like the scale of a river or a large creek, which is often what's gauged by USGS, At that scale, we have less confidence we'll be able to see sort of increases in flooding, just due to the difference in sort of processes and controls. But sort of understanding, which basically took a half hour for me to talk through that, understanding that distinction helps us make sense of, can we have increases in precipitation? Can we have increases in flooding at one scale, but not another? Okay, so what I just want to finish with is just, given that there is still some amount of uncertainty, say with flooding, but also other elements of hydrology, meteorology in terms of how that'll affect climate, is can we still make decisions? I think, especially among scientists, there's this sort of tendency to say, well, if we don't quite know the answer, then maybe we should keep studying it and we should keep waiting until we have a better chance of knowing what that answer is. But the reality is we can't be paralyzed by not knowing exactly what's going to happen. So there's really pretty, standard strategies to get around this. First one is to think about, how do we diversify and how do we add redundancy in whatever we do? I think lots of people already do this. If you're a farmer, instead of having one type of crop, you might have multiple crops. Instead of having two fields that are right next to each other, you might spread your fields out in multiple locations. So if one field gets washed out, the other one doesn't. And we can think of this for all sorts of things. If you are relying on a water source, it might be good to have two different well fields that aren't right next to each other instead of one well field. The second thing we can do, even in sort of the face of uncertainty of how things will change, is to still recognize there's some factors besides climate that make us more sensitive to disruption. So this goes back to sort of thinking about, this is why we identified floodplains. Even if flooding does or doesn't increase, if you're building in the floodplain, you still have a much more likely chance of being impacted by flooding. Another approach is other new modes of planning and coordination. I didn't really have time to get into this, but one element of this, I only talked about flooding, but one reality of this is basically thinking about changes in water level over longer timescales. So where flooding is happening in a matter of days or hours, there's a lot of thinking about how will overall lake water levels change over sort of weeks to months. Part of dealing with that, especially in the Finger Lakes, here's my other slide for this, is just to acknowledge, I think a lot of people know this, is you can't just open the spigot at the end of Seneca Lake and the water immediately exits somewhere, is you basically have to coordinate. The water from Seneca Lake goes to Keyu Lake, and then the Seneca River, and then the Oswego River, and finally Lake Ontario. So there needs to be coordination about how do you move that water through these other systems and control the water levels in Seneca Lake. My sense is there's still not that much, coordination about that type of thing, but it's certainly something within the realm of engineering and planning and science to better coordinate there. And then final thing, even if we're not quite sure what's going to happen, is just to recognize climate as one of many stressors on the system, such as the Finger Lakes, which others include nutrient additions, land use change, which in the end are probably things we can control more than we can control climate. So even if we can narrow down how things might change in the future, there's still going to be a certain amount of uncertainty, but there's ways to deal with that uncertainty. Okay, and I'll end there.
That's awesome. Thank you so much, Steve. We do have just one question in the chat, and I didn't mention earlier that if you have questions, please use the chat box, and then I'll direct them to Steve to answer. So the first question we have is from Meredith. Do you have any information about the Susquehanna River Basin, which seems to flood readily, at least between 2016 and 11?
Yeah, it's a little bit the same story of sort of the Delaware, which isn't that far away. Is we had those events in 2006 and 2011 caused by a little bit, I think, different, have to look at that, kind of different causation, but it's sort of not an upward trend. A lot of these, if you look at these larger river systems in New York, which I've been doing for some other work, there's really not many that show much of an upward trend. So, some of these, it's just sort of coincidental. You might have two events, pretty high flow events that happen near each other. I think over the long term, you'll see some slight increases in peak flows, but nothing sort of at a catastrophic kind of level where it goes from being one thing to twice as high.
Okay. Let's see. Oh, now they're coming in. Let's see. I'm new to Finger Lakes. Do canals ever flood?
Let's see. Do the canals ever flood? So canals are complicated. I've done quite a bit of work on the canals, I guess. Part of it is sort of, so the canals, if you look at, say, this canal in central New York is connected to the Finger Lakes. So this is sort of went back to this idea of sort of managing water levels in Seneca Lake. If you release water from the water levels in the Seneca Lake, it raises the water levels in the Seneca River, which is part of the canal. So yes, then the canal can start to flood. But it's one of these things where there needs to be coordination across all those entities to keep that from happening.
Yeah. Can I say something? We certainly, can you hear me?
I can.
Yeah, we certainly saw this November when the Seneca Lake was so high. Highest water level I've ever seen anyways at my cottage, and didn't realize where the controls flow to and from. But I think I understand now that it's all canal related, right?
Well,
But
and the issue, it's always this issue of you don't want to not have enough water in the lake, but you also don't want to have too much. And I think part of it, I was looking at some early documentation, well, not early, 20 years ago, in terms of people thinking about managing those water levels. And it sort of acknowledged at the time that they thought that meteorologists could only predict rainfall accurately about 2 days out. I actually think that's quite a bit improved now. It would be interesting to revisit that basically, could you basically try to predict rainfall with a farther lag time, so say a week out, in terms of what you think is going to happen, and then respond sooner to releasing water from the lakes.
yeah. Well, now the lake level is very low, the lowest I've ever seen. It's out like 20 feet low from my dock anyways. So it went from too high to too low. So I hope they can, bring that level up. So, boats coming into boat lifts and all that can get in there. Okay.
Yeah, I mean, it's one of those things where some of it's you can regulate and some of it's dependent on what the weather's doing. I'm going to look at a few other questions here. Let's see. So there's a question about potential drought. Yeah, I didn't really talk about drought. I basically focused on flood, but I didn't get onto that side of things. But I think drought's a little harder to predict, but especially short-term drought, which a drought lasting sort of months, 2 months, 4 months, things like that, it's likely that there'll be more drought. Part of that is due to increased atmospheric demand, which basically means the growing season is longer and it's a little hotter. So vegetation and plants are using more water themselves. So you're drying things out.
If you want, keep
But
going.
we haven't.
Yeah, I'm going to keep going here. Let's see. Do you have any information on climate change has impacted wildlife, specifically birds? I'm not a bird person at all. I'm sorry. So, but you'd have to. But I'm sure there's definitely wildlife biologists that are looking at that type of thing. Let's see. And let's see. Hi, John. So from John Hackman, can you comment on the high lake levels in Seneca and neighboring lakes this fall? I haven't been looking at I wasn't paying attention to that, but overall, I didn't quite get into this either. I just sort of talked about high intensity sort of events, but overall the projection is that things will get wetter. So I don't think it's necessarily surprising. I mean, in all these systems, there's a fair amount of variability, year-to-year variability, but most of the climate projections are basically saying that things will be wetter. And also just based on that sort of the Clausius-Clapeyron relationship, saying if the atmosphere can hold more moisture, in general, when it rains, it should be a little more rain. In aggregate, that sort of suggests things should be a little wetter. So probably, that probably is generally the upward trend. Let's see, the question, 71% increase in precip in the Northeast. I'd have to look at the details of that paper, but that was probably sort of mid-century to end of 20th century, something like that. Let's see. Okay, a question on, is it possible the watersheds of the Finger Lakes evolving from orchards and cornfields into more vineyards are causing more runoff versus retention? That's an interesting question about how vegetation and land use affect runoff. I did a study a number of years ago where I actually was looking at, does reforestation sort of cause changes or visible changes in stream flow records? So, in some cases you do have land use transitioning from, say, corn into vineyards, but actually the acreage of that isn't that much compared to if you look at pictures of, say, the Finger Lakes or Cayuga Lake 100 years ago, there's like not a tree to be seen anywhere. And really the more dominant change is that you actually have a lot more trees in reforestation. With that, you might expect trees to more efficiently use water and actually cause less runoff. There actually wasn't much of a visible change in the records that were available. I think that's partially just the fact of just sort of how the hydrology of the systems, that even though you replaced farms with trees, they both kind of use the same amount of water. And then also, I guess, this idea of runoff, do farm fields cause more runoff?
Yeah.
Not necessarily. So the soils around here generally are pretty pervious. And whether you have trees on those or whether you have corn on those, the soil is still pretty pervious no matter what. It's going to accept water pretty well. Different story if you go to like the farther than the Midwest, but like this Nebraska or places like that, you start to get, or Oklahoma, you get more clay in your soils, and they really can not accept as much water. But around here, like really the ability for the soil to infiltrate water is much higher than most rainfall rates, even for what we think of as a really intense storm event. Oh yeah, and then here's a question on reforestation. Could it be moderating peak flows? Probably at the time scale of flooding, probably not. If you looked at long-term averages, it's possible. And I should say too, so there's probably other changes in these systems, engineered changes. I do know, like in Fall Creek, there's no mention of this in the USGS notes, but I do know they added a flood control dam in the upper reaches of Fall Creek in 1998. So there's certain things here that is actually a number of dams, like there's a big dam, but if you start to look at dam records and maps of dams, you realize there's lots of small dams and watersheds, possibly hundreds, just these little ones you don't normally think of, but every pond or small pond that basically adds some retention. So it is possible that actually construction of small dams, even just farm ponds and things like that, actually cumulatively could lead to some more retention of water in these systems. Let's see, what can we do as residents on Seneca Lake to help reverse the effects of climate change? I think in some ways, how do we actually mitigate? How do we minimize climate change? I think in some ways being an adopter of technologies that reduce energy consumption, right? So I think 10 years ago, it would be hard to say, go get an electric car, but if you're in the market for a car and can afford an electric car, it might be something to consider. Same thing for heating. Now in terms of heating and cooling, you can get heat pumps that basically are pretty efficient. I know we just got a new hot water heater, and that's a heat pump hot water heater. It'll use less energy over time. So those are sort of incremental things, but if everyone did that, it actually would add up. And I don't show this in a slide, but I showed to my students. In the US, the amount of energy consumption has basically been flat, if not declining, for the last 20 years, right? It needs to go down a lot more than it is, but by sort of adoption of technologies, we have basically at least kept energy consumption from going up.
Steve, I think one question above that you may have missed, the 71% increase in precipitation in the Northeast was over what period? Did you?
Oh yeah, I think I'd have to look at the paper. We could look that one up, but I think it's probably like the middle of the century to the end of the century, something like that.
Okay.
Yeah, the last 2 years have been very wet. Last 2 summers.
So, and I see the question about the points in the lake. Yeah, I would actually be interested. I was sort of, so someone asked about or disagreed with my interpretation of how long the points had been there. And that's fine. I was saying I'm not a geomorphologist and I don't know. I'd actually be really curious to know what form those and can we relate those, to what degree is it the streams that are there and what degree is it other processes? But this person was saying that some have been there more than 1,000 years, which is actually really interesting. Thanks for thanks for offering that information. Yeah, I was a little probably too speculative there, but I couldn't resist just looking at the image when I looked at it in Google Maps last night. Let's see, a question about what about the value of increasing riparian buffer zones in reducing runoff? I think they have value, riparian buffers. I think this is my slightly, I guess, jaded view on things sometimes. There's certain things we do because just to say we did something. I'm not always convinced that riparian buffers really do that much. I think in terms of really severe erosion or things like that, I think they can help trap that really severe erosion. But I'm not sure if all the time it's the answer to everything. But I don't want to say, I mean, any case where you're basically, so as a quick example, I know in the Delaware watershed where that supplies part of New York City's water supply, one thing they found is, so people were pushing riparian buffers. The biggest effective riparian buffers was when farmers would let cattle stand in their stream. And really is more the cattle standing in the stream, disrupting the stream and just generally, directly moving soil around. That was the biggest issue. And by saying, okay, let's have riparian buffers, that got the cattle out of the stream. And that was actually probably the thing that made the biggest difference. So so I think there's sort of unintended consequences in that. Okay, questions on varying lake levels. Yeah, and someone mentioned, I'm not a specialist on this or an expert on this. There is sort of what's called a rule curve, which is sort of intended to indicate how you should be regulating water levels at different times of the year. My thinking on that was, I think that same rule curve has been around a long time. And it would be interesting to revisit that in sort of light of what we know now about climate change and also our ability to predict weather, precipitation events with a longer lag time, a longer time out, and reconsider, should that rule curve be updated in some way?
Yep. Great. Agree.
Okay, thanks for that. Continued, so I'm going through continued questions here. Continued mention of the points in the lake, which, yeah, I'd be interested to talk about that more, but I probably was wrong. Let's see, your title had forestry in it. Yeah, let's see. Looking at, so right, there's the CLCPA, which is sort of the ongoing climate, well, they recently implemented Climate Act to reduce New York carbon emissions by a huge amount by 2040 or 2050, where there's this push to use more wood products. I haven't read the thing really much at all, although I've been meaning to do that. So, okay, and I think, I don't know, did I reach the end?
I think so. Well, yeah, it looks like that's the end.
Yeah.
A lot of questions, a lot of good questions. Well, if there are no other questions, Steve, thank you so much. Like I said, there's a lot of different types of interested parties in this presentation, and you covered a lot. This presentation has been recorded, and so if anybody would like to, look back at it, or if you missed the beginning, you're welcome to view that on our YouTube page in a few days. Actually, it looks like John Halfman has raised his hand. John, do you have a question you want to ask Steve?
Oh, did it by accident, sorry.
Oh, okay. But yeah, Steve, thank you so much. And, I'll get everybody the YouTube recording and Steve's link to his research page. And, Steve's also doing some research on localized tabs, like I mentioned earlier, which we're always interested in hearing more about. So, yeah, thank you so much, Steve.
And I'll also mention real quick, I'm the lead co-author on the New York State Climate Impact Assessment for water resources. So if people have specific, especially information, sort of on the ground information they want to pass on, I'm happy to sort of take that and see if that can be integrated in this climate assessment. So,
Steve, is there a link we can use to?
My ESF email would be the best thing.
Okay, I'll do that. I'll share that with the group. All right, great. Thank you so much. Thanks everybody for joining.
Thank you. Thank you very much.
Have a good
Thank
night.
you.